Hi, here we're going to present our final project. Our topic is current number of COVID-19 infections and future trends. My name is Huixin from Computer Engineering of UNIO.
I'm Wencheng from College of Art and Science from University of Nebraska Lincoln.
I will use the first 10 minutes to introduce our motivations, tools, datasets, and my work. Wencheng will use next 10 minutes to introduce his work, our model evaluations, and our future planning. The reason why we choose this topic for our final project is because we are facing a situation where we cannot have classes because of a pandemic. As we know, since the outbreak of COVID-19 in the United States last year, many universities have closed their campuses in order to prevent the spread of COVID-19 among teenagers and affect the health of students. As a result, many students cannot attend classes in school, and many international students cannot even come to the United States to complete their studies. This year, several universities announced plans to open their campuses in the fall semester and began face-to-face teaching. However, there is still a huge number of people infected with COVID-19 in the United States. So the decision to completely open school is still risky. So our goal is to predict the number of COVID-19 infections and the rate of increase in the number of COVID-19 infections per week before school starts in the fall semester, and to say if it was a good decision to start face-to-face classes in the fall semester. The methods we use are function interpolation methods and least square approximations. We are using Python 3 to programming, pandas to read our data files, NumPy to deal with the matrix operations, including matrix transpose, multiplications, addition and subtraction, and the Matplotlib to draw images and the models. Our data is presented here. We collected the number of new COVID-19 cases in the United States each week since February 3 of last year, as well as the total number of people currently infected and cured. The data collected from University of Johns Hopkins. This is our GitHub link pointing to the original COVID-19 data from University of Johns Hopkins. This is our data performance and manipulations. The first picture shows cumulative diagnosis each week. It is an increment function. The second picture shows weekly increase. It is a wave function. The third picture shows cumulative diagnosis each week. It is also an increment function. We will use time as an independent variable. The weekly increases, cumulative diagnosis, and cumulative cure as dependent variables. And we will use two different methods, function interpolation methods and least square approximation to modeling cross data from week 1 to the week 56. And then we will use RMSE to evaluate different models to find the highest value model. We will forecast the model of week 57 to week 60 and compare it with real data by calculating the accuracy. We will find the best model under different conditions. and use this model to predict the weekly increase and the total number of COVID-19 in United States at the beginning of the fall semester. This is our Python code for interpolation method to predict the future weekly increase. In order to make our predictions relatively accurate in interpolation methods, I choose data only after the vaccine began to be used in the United States. Those two pictures are the methods of Lagrange interpolation and the Neville methods. They are based on the source code on our textbook. Here, the x in the Lagrange interpolation is interpolating point that we want to get the predicted weekly increase in week 6. The n is the length of the list of our independent variables. Here, the xt in Neville method is the independent variables. And the m is a two-dimensional matrix to store our calculating values. N is the length of the list of our independent variables. The x is interpolating point that we want to get the predicted weekly increase in the week x. Those two pictures are the Newton divided method and the cubic spline interpolation. The x in Newton divided method is list of weeks. Y is list of weekly increase. And the capital X is interpolating point. The xi in cubic spline interpolation is the list of interpolating points. X is weeks. Fx is weekly increase. And it will return a list of predicted weekly increase. Here is my results from those 4 methods. The first picture is the result of Lagrange interpolation. The second picture is the result of Neville methods. And the third picture is the result of Newton divided method. The last picture is the result of cubic spline interpolation. From those predicted value, we can see the predicted value of Lagrange interpolation, Neville method, and the Newton divided method for week 61 is close to 600 million, which is larger than US population, so it is impossible. And the predicted value of cubic spline interpolation for week 61 and 62 are negative number. So it is also impossible. According to our data analysis by using Lagrange, Neville, Newton divided methods, and the cubic spline interpolation, we think for our dataset, interpolation methods may not be good methods for us to predict the value outside the interval.
Therefore, we think that the interpolation method may not be suitable for prediction here. This is maybe because we use high-order interpolation polynomial, which is unstable, and the data itself may have errors, and the interpolation polynomial obtained by interpolation will also retain errors. This can lead to large errors. So that therefore, we intend to use the least square for prediction. The reason why we use the least square for prediction, this is because we think the prediction is kind of data fitting problem. Generally, the approximate analytical expression is not required to pass through all known points. So about least square method, it's just asking to go through their neighborhood point. This can offset the error in the original dataset. Next, I will introduce 3 different least square methods we use and show corresponding Python design concept and writing method. The first we introduce is the linear least square. This is also a linear regression algorithm. Our goal is to find the value of a and b in function y equal to ax plus b. The method we use here is matrix multiplications. First, we will get the matrix A and multiply with the transpose matrix A and find the inverse and multiply the transpose matrix A and multiply the matrix Y. Here is our math formula, and this is our Python code about how to accomplish this math formula. We will contribute the matrix A by using x and 1, and we will find the matrix F, and we will find the matrix A, and we will multiply the matrix A and the A and find the inverse and multiply the transpose matrix A and the matrix Y, so that we will get A and B, so that we will get the function y equal to ax plus b. On the right-hand side, there is a comparison between the original data and our forecast data. On the above graph, this is about our weekly increase, and the lower graph showing the cumulative diagnosis. At these two graphs, we can see that the blue dot line is the original data, and the blue line is our prediction data. Here we can find that the result we get here is quite different between the original data and our predicted. The next, we will go into the polynomial least square. At this time, we will go through the polynomial least square with degree 2 and degree 3. For the polynomial least square with degree 2, we will find the A, B, and C to solve the y equal to ax squared plus bx plus c. And the way we're going to solve this question is also by using the matrix multiplications, by finding the matrix A and multiply the transpose matrix A, find the inverse, multiply the transpose matrix A and Y. At this time, we can contribute the matrix A by 1, x and x squared. And then we can find the transpose matrix A and do the calculations. And finally, we will get A, B, and C to satisfy this formula. At this time, we can go in through the prediction graph right here. For the weekly increasing, we can see that through there still have several points. It's quite different with actual point and prediction point. But at the beginning of the prediction, we can see that our prediction is closely on the. We can see the actual point is actually on our prediction line. And for the cumulative diagnosis, we can see that there are several points looks like it's on our prediction line, which means maybe the polynomial least square with degree 2 has a better performance in the cumulative diagnosis prediction. And then we will going through the polynomial least square with degree 3. At this time, we will find the A, B, C, and D. We will also using the matrix multiplications by using A times transpose matrix A and find the inverse, multiply the transpose matrix A and the matrix Y. At this time, we can contribute the matrix A by using 1, x squared, and x plus 3. And then we will find the matrix A, transpose matrix A, and do the calculation so that we will get A, B, C, and D. At the graph on the right-hand side, we can see that through that in the weekly increase, there are several points are different, but our prediction is showing a downtrend, and the actual data is also showing the downtrend. This is a really huge improvement, because in the linear least square and the polynomial least square with degree 2, both of our prediction is always showing the constant increase. And for the cumulative diagnosis, we can see that looks like most of points, actual points, is on our prediction line, which means the polynomial least square with a degree 3 has a really good performance in the both of weekly increase in prediction and the cumulative diagnosis prediction. The last least square we use is exponential least square. We are going through the equation like the y equal to a times x. At this time, we also use the matrix multiplication, but at this time, we are going a little bit a change in the how we can get the matrix. We will firstly get the matrix A by using the 1 and X, and next we will get the matrix B by using Y and X multiply Y, so that we will also get the transpose of the matrix B. So we can multiply the matrix A and B first, find the inverse, multiply the transpose matrix B, and multiply the matrix log Y, so that we will get A and B that we require. And here are the two our prediction graph. And for the weekly increase, we can see that through there at the beginning, there are several points look like it's on our prediction line. However, the trend is constant increasing, but the actual data is decreasing. In the cumulative diagnosis, the prediction looks is really good, because we can see that almost looks like all of the point is on our prediction line, which means we think the exponential least square is doing really well in the cumulative diagnosis prediction. Then I'm going to introduce our model evaluations. We are all using the two model evaluation. One is RMSE and another one is R-square. First, it's a root mean square error. The root mean square error is the square root of the ratio of deviation between the prediction value and the true value and the number of observation n. In particular measurement, the number of observation n is always limited. At this time, we have observation n equal to 56, and the truth value only be replaced by most reliable value. The similar, the smaller RMSE is, the better the performance of the model is. Here is the math formula for how we can get RMSE, and this is our Python code to get RMSE. We use our prediction value minus the actual value and find the square, find the mean value, and find the square root. And next one is R square. The R square is a closed range of 0 to 1, which is a kind of index to evaluate the quality of fitting. We know that if we get the R square, it's more closer to 1, which means our regression equation is have a really better quality of fitting. And here is the formula about how we can get the R square, and this is a Python code about how we get the R square. We use our actual value minus the prediction value, and we can find the square and find the total sum. And to divide the sum of we can use our actual number to minus the mean value of the actual number to get the square and to find the square and find the sum. Then we will use 1 minus the whole thing, so we will get the R square. And now we can show the RMSE and the forecast for weekly increase first. Since we have introduced that if the RMSE is smaller, which means the model will have a better performance. At this time, we can find the smallest RMSE is belongs to polynomial least square with a degree 3. It only have 267,665. At this time, we know that the polynomial least square with a degree 3 have the best performance in the forecast for weekly increase. And we find the R square value is 1.0, which means polynomial least square with a degree 3 is have a really good quality of fitting the weekly increase in original function. And next page is about the RMSE and the forecast for cumulative diagnosis. At this time, we can find that the smallest RMS value also belongs to the polynomial least square with a degree 3. At this time, the RMSE value of polynomial least square with a degree 3 is only 741,294. And the R square is also 1.0, which means polynomial least square with a degree 3 is also have a really good quality of fitting in the cumulative diagnosis original. So that if we recommend the one way to predict the COVID-19 something or do some prediction calculation, we will recommend to use a polynomial least square with a degree 3. This is because a polynomial least square with a degree 3 has a better is a better performance in both of the for case for weakly increasing and for case for the cumulative diagnosis. Then I'm going to talk about something about our final result and our future work. At the beginning of the first semester, it's at August 23, we have the weekly increasing is about 177,287 by using polynomial least square with degree 3. And we can find the total number of COVID-19 it's about 40 million and 711 and 457 by using cumulative diagnosis minus cumulative curve. We are going to use the polynomial least square with degree 3 to predict the cumulative both of cumulative diagnosis and cumulative curve because we find both of cumulative diagnosis and cumulative curve have the constant increase in depth. So that based on the value we predict, we think maybe it is really dangerous to reopen the campus on the beginning for the first semester. And if the people want to do some prediction work or also about something about the COVID-19, we are going to recommend the algorithm. It's a polynomial least square because polynomial least square is have a really good performance in both of the cumulative diagnosis and weekly increasing predictions. Then I'm going to talk about something about our future work. We're going to use logistic and autoregressive model in the future because we think that at this time we'll only use linear regression. Maybe just logistic and autoregressive will have a better performance. And then we are going to try to narrow the scope of the data set to forecast and compare, such as using monthly data to forecast. This is because we find there are several months data it shows really spring. Maybe if we can try to narrow the scope of the data set, we will get better performance of our prediction. And third, we are going to try to predict what will happen after everyone is vaccine. This is because we think the vaccine will have a huge influence to the COVID-19. It will greatly decrease weekly increase. Yes, so that maybe we can get a more accurate forecast for COVID-19 when the semester starts in the fall after our combined vaccine forecast. Thanks for watching and listening.